Okay, this lecture is on reflections. A reflection is a transformation that uses a line, like a mirror, to reflect a figure, and the mirror line is called the line of reflection. So here we see that we have this image, and line M is our mirror, and it is reflecting point P from one side of the mirror, and the reflection is P prime. Now, what we want to notice is there's two very important things being shown to us here. One, a reflection travels on the perpendicular line through the mirror, and two, we see these congruent marks showing us that the pre-image and the image point are equidistant to the mirror. So those are the two important properties of reflections. Now, for anyone that is not familiar, this symbol means is perpendicular to. And these are the two properties that we will be constantly monitoring as we reflect points through a line of reflection. Now, before we go on, reflections are also known as flipping a figure through the mirror. So when we reflect something, we get a flip of its image. And just to give you a quick demonstration, if I have this image here and I flip it through line M, I expect to get equidistant points from the mirror. And when we're done, we see that the pre-image and the image are flips. So we see that this has the curved edges to the left, and this has the curved edges to the right. So we kind of flipped it over the line. So here in our first example, we're asked to graph triangle ABC. So we see that point A is at 1, 3, point B is at 5, 2, point C is at 2, 1, and we're going to reflect it through this line x equals 3. And what we want to remember is we have to move perpendicular to the line and equidistant. Well, this is 2 units from the mirror along a perpendicular path, so I expect A prime to show up right here. And I'm going to remove that perpendicular segment so that it doesn't make the image too busy. And then we would do the same thing with B. We would take it perpendicular. We see it's 2 units again, and that would bring us to right here to get B prime. And I'll take that perpendicular segment out so that the image doesn't get too difficult to follow. And we see that point C is 1 unit away from the mirror, so we bring C prime over there. Now we can connect these points together. And we see here that the reflection produces an image that is on top of the pre-image, and that's because part of the pre-image was on the left of the mirror, part of it was on the right, so we get this type of scenario. So here in this next example, we are reflecting over the line y equals 1. It is a horizontal line, and we see that point C is on the mirror, so point C will be its own reflection, and that gives us C prime. When a point is on the mirror, it is its own reflection. Point B, we will move perpendicular to the mirror and equidistant, so we have our B prime. And we'll do the same thing with A. To get A prime, it is 2 units away from the mirror. So we'll move 2 units on that perpendicular path. And when we connect these 3 points together, we get the reflected triangle. Now we have a line that is slanted. And this slant line, y equals x, has a slope equal to 1. So if we're going to move perpendicular to this slanted line, we need to move with a perpendicular slope in mind. So recall, perpendicular slopes are negative reciprocals of each other. For example, 1/2 is perpendicular to -2/1, or we can say 5 is perpendicular to -1/5. So for our example, 1/1 is perpendicular to -1/1. So if we draw the perpendicular line, which has a slope equal to -1 through point G, and we can say, well, notice how point G is half a diagonal away from the mirror. Well, equidistant means it'll be a half a diagonal on the other side of the mirror. And we can name this G prime. And we can use this same path with F. We can see that F is 1.5 diagonals away from the mirror. So we can then count 1.5 diagonals on the other side to get F prime. And then we can connect these 2 points together to give us the reflected segment. Something we can notice here is that G prime has coordinates of 2, 1. But notice that G had coordinates of 1, 2. And F prime has coordinates of 2, -1. But notice that F had coordinates of -1, 2. What we should see is in this pattern that the x and the y coordinates were simply switched, and we're going to discuss some of these shortcut rules in the following slide. So far, the reflections we've done have been accomplished through moving our points along a perpendicular path equidistant from the mirror. That is the construction way of performing a reflection. There is also a motion rule way. We can rewrite each of these rules for reflections using the same type of notation we did with translations. So this first rule, we can say that the point xy gets transformed to the point x negative y. So look at that. The AB becomes A negative B, and this is only true when reflecting across the x-axis. So that gives us a rule, a motion rule, for reflection across an x-axis. And we can write each of these rules using this type of format, which we are already familiar with from our unit on translations. So we've written a rule, a motion rule for each of these scenarios, and we can even give these a verbal description. When we're reflecting across the x-axis, simply change sign of y coordinate. If we're reflecting across the y-axis, then we simply change the sign of the x coordinate. And if we're reflecting across the line y equals x, switch the x and y coordinates. And if we're reflecting across the line y equals negative x, we will switch the x and y coordinates and change both signs. And these rules are good for these scenarios, but if we have scenarios different from this, if we're not reflecting across x or y, or the line y equals x, or the line y equals negative x, then we go back to our construction approach where we follow the perpendicular path equidistant from the mirror. So in this next example, we take a look and we see we've got the line y equals negative x. This is one of our 4 rules. This one says that x comma y becomes negative y comma negative x. We're going to switch the coordinates and we're going to change the sign. So we see that point F has the coordinates -1, 2, and that means that F prime will have the coordinates negative 2, 1. So notice that we switched 2 to the x and changed its sign to negative 2, and that we switched negative 1 to the y and changed its sign to positive 1. So we have that switch and changing of both signs. G has coordinates 1, 2, and when we reflect it across this line, once again, we're going to switch the coordinates and change the signs. So now if we plot these points, f prime is at negative 2, 1, and g prime is at negative 2, negative 1, we can see that this follows a perpendicular path and is equidistant. They are each a half a diagonal away, and the g's are on the perpendicular path and equidistant. They are each 1.5 diagonals away. So we've got the construction approach verifying our formula approach, and the formula approach is much easier to do. So whenever possible, use those rules, and we'll get the coordinates easier and quicker. So here we have a postulate. Just a reminder, a postulate is a statement that is accepted as true without any type of proof. That means with very little reasoning, we can come to an agreement that this is something that we can accept as true. And here we have the reflection postulate, which states that a reflection is a rigid motion. A rigid motion is a transformation that does not change the size or shape of a figure. And when we say it does not change the shape, it does not change the angles. Not the number of angles, not the size of the angles. So because a reflection is a rigid motion, we can see that this triangle over here, the pre-image, is congruent to this triangle over here, the image. And that not only are the triangles congruent, but each of their corresponding parts, if you look at the angle D and D prime, if you look at the angle E and E prime, the angle F and F prime, those are all congruent, so are their corresponding sides. And this is going to be something we use a lot in the units to come as we start to prove congruent figures. Another topic in this section is the definition of a glide reflection. A glide reflection is a special composition of transformations. Now, you can transform by translation and reflection and not be a glide reflection. But if you do it in a specific way, then it's a glide reflection. So let's read through this. It is a transformation involving a translation followed by a reflection in which every point P is mapped to point P double prime by the following two steps. First, we translate P to P prime. So these are our vectors here. Then we have a reflection in line K, but line K is parallel to the vectors. So we see here's our reflection line, and notice they put these triangles here to indicate parallel. So the line of reflection must be parallel to the vectors to be called a glide reflection. So it's a special type of composition where the reflection line is parallel to the vectors. Here is an example of a glide reflection. So first we will translate. We see that this rule says move 12 left and no movement on the y coordinates. So we're going to take this and move everything over 12 units. So if this is triangle, this is the image of the triangle after the translation. And then we can do the reflection of this triangle. And this would be triangle double prime. So we see that we did a translation to the left, and that this vector is parallel to the x-axis, which we reflected over, and that's the reflection part, so they're parallel. And when we reflected, we got this second triangle, and that this is the result of a glide reflection, because the vector that translated the triangle was parallel to the mirror that reflected the triangle. And finally, to wrap up this section, we talk about something called lines of symmetry. Here it says a figure in a plane has line symmetry when the figure can be mapped onto itself by a reflection in a line. So what does this mean? This means that if I draw a line through this figure, notice that this point will map onto itself and vice versa. This one will map up on top. And if we do that, we'll say, can you tell the difference between the pre-image and the image? And the answer is no. So when the pre-image and image look the same, after a reflection, the figure has line symmetry. And we see that this first figure has two different line symmetries. So if I map the left points to the right and vice versa, they land on top of each other. If I map the top points to the bottom and the bottom to the top, they land on top of each other. So we have two different types of line symmetry here. For B, we have line symmetry on these three diagonals, but then we also have line symmetry through the midpoints of the sides. So this one has 6 different types of line symmetry. And for C, the only line that will make this reflection land on itself and be indistinguishable is this horizontal one. So this one has 1 line symmetry. Okay, so that is the end of this lecture. You can go back, watch it again, take notes, and write down questions to bring to class.